Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so let's get started. It's my pleasure to introduce Professor Ying-Li Tian. She's from City University of New York, and she's also visiting us for 2 months. And before joining City University of New York, she was a researcher at IBM, leading the effort on the smart surveillance system from the initial research project to a commercialized product. So it's really a big effort. And before that, she worked at CMU for quite a few years on the facial expression recognition. And that's probably one of the main part of the talk. And before that, she was a professor at the Institute of Automation, Chinese Academy of Sciences in China. Yeah. And please.
Okay, thanks to you. So I'll start to talk about the automatic facial expression analysis. Part of the work has been done when I was at CMU. It's about, I think, 10 years ago. But after that, I continued work on that until 2004. Then for the IBM project, the people wishing the surveillance system getting, with more and more priority. So all the focus shifted to there. So I stopped to do that. Since now I came back to the academic, so I have more time to pick up this topic again. So I'll talk a little bit for the future work at last slides. Before I go to the details about the work, I want to give a list about the applications for the facial expression. Many people work on this, but still do not see the real application on it. Some future applications, I think we can do the emotion and the paralinguistic communication, and also for the clinical psychology, psychiatry, and the neurology, and also can do the pain assessment. People also can do the lie detection. When I was in CMU, I think that's in 2000, CIA organized a computation between the CMU and the Salk Institute, who did the expression analysis to see which system can really deal with for the lie detection. And also can be used for the person identification. For this one, since some people, their expression are very unique. I have one colleague, his neutral is like this. So this kind of feature can be used for the person identification. And also we can do the image retrieval and the video indexing to say, okay, can you find all the Clinton's picture with a smile, something like that. You can put this information in. Then for the HCI and the intelligent environments. And also when we talk about the driving awareness, this is only a subset part of the facial expression. When you droop, when you're sleeping, only for the upper part of that can be used for the driving awareness. Please feel free to interrupt me if you have any questions. For the general steps for the automatic expression analysis, I classify them for these three. The first one, we want to find the face. Where is the face? Only when we find the face, then we can do the facial expression analysis. After we find the face, we will do the feature, data extraction, and the representation. Then we will do the facial expression recognition. For the face, most of the lab control environment, people use the face detection. But in the real life, you cannot get the face directly. So in my talk, I also talk about for the head pose estimation, try to find where is the head, then focus on the front of the face. For the feature extraction, people mainly can use two kinds of features. One kind of feature I call it geometry features. That means people extract where the eyes, the lips, and the nose, all those kind of features. For the appearance features here, I mean is give you the face after you detect it. You have the whole face. You just find the feature for the appearance of that. Maybe use the edges, maybe use the Gabor filter, maybe use all some other features you get from that face region. For the facial expression analysis, people work on two paths. One path is called the basic expressions. These basic expressions, I'll give you some example in next slides. And also another part is for the action units. The 6 basic expressions mainly give you the whole face to say, okay, this expression belongs to the anger or happy, something like that. For the action unit, it's more subtle to correspondence to the some points on your face. Okay, here are the 6 basic expression. We call it 6 basic expression because it doesn't matter which culture. Doesn't matter you are male or female. These 6 class of the expressions are pretty universal. Disgust, fear, joy, surprise, sadness, anger. I'll also show you some action units. The facial action units was coded by the psychologist. Mainly, they have the different part of the face. For the upper face, we have 12. Lower face, we have 18. Then they have the eye and head positions and some others. For our talk, people still mainly focus on the upper face, lower face for the face action unit. And also, we can see for those kind of action units, for the real life, they have more than 7,000 different combinations by combine those kind of. So our goal is not only recognize the single action units, we also need to deal with the combinations. Here are some examples here. So AU1, for example, they say, okay, for the inner brow of this, you can lift it. That's the AU1. Then they say, okay, for the out part, this brow, you can lift it up. That's the AU2. Paul Ekman, they can do that. He's the famous psychology guy to develop the action unit. But most of the people cannot, only lift the inner part and then lift the outer part. So we mainly move them together. If you move your brow up together, then that's AU1 plus AU2. I gave some examples here. You can see some in red color. Those in red color means we didn't recognize them in the system because either we do not have enough data in the database, either they are pretty confusing. For example, this AU42 and the AU44. So AU43 is a closed eye. When you close it, it's AU43. But AU42 is when you drop down your upper lid in halfway, that's the AU42. But when you do the quint like this, that's the AU44. For those kind of actions are too confusing, so I didn't put them in the system. Okay, why the facial expression is difficult? I give you some examples here. You can see this is AU13 and AU14. One is a cheek puffer, one is deeper. But from the image, it looks very similar. But they code as 2 different AUs. And also, if you can see this two, is AU12 plus 25. AU12 means you lift your lip corner up. 12 means you open your mouth like that. So when you put that together, most of for the smile, if you do this, it's the 12 plus 25. But for AU20 plus 25, the AU20, you just stretch your lip, but do not lift your lip corner. So, but when people are doing it, it looks very similar. And also another example is AU10 and AU9, both shows disgust. But for the AU9, you can see here, we have furrows here. If you have furrows here, the code is AU9. If not, they code it as AU10. Yes?
Should I think of an action unit as being like a parameter or a state of,
They say, okay, if you have the neutral face, like this, then you do this kind of facial movement. When you move like this, then for each movement, they give one code. They code it as the action unit. Then for the different kind of movement, they give a different number.
But is it is an action unit it's
it's a localized motion on the face.
Okay, so not the state
Not
after the motion, it's the degree along which you move?
No, the degree, if this is my neutral, if I do this, that's one kind of motion. Then they have this kind of, for example, this 12, AU12 is set like this. I move my lip corner up.
I think of it as the action unit is, one action unit is to be able to move the corners of my lips up.
Yes.
Okay, not the state of having my lips moved into that position.
No.
Really? I mean, for me, I think the action unit is the state, right? When you raise your eyebrow, that's
the state of being up.
Yeah, that's
as opposed to the muscle or whatever that moves, that eyebrow up.
No, it's not the motion, it's the fact that it's up. So that's the action unit present on your face. Am I?
So the movement caused by facial muscles. I think you can also see there's a state after when you compare to the neutral. If I move this one, this is the AU1 plus 2. So that's the code to see this kind of state and the movement. When you see how much is movement, they call the intensity. They also have another parameter called action unit intensity. If that intensity is big, for example, if I open my, I'll show you some example like this here. If we go back here, you can see we have the, where is it? AU25, this is 25, this is 26, this is 27. For now, this is the previous one. They code it as 3 different actions, but the main difference is how big you open your mouth. For this one, it's only a little bit part. They call it AU25. If you open larger with bigger intensity, they give a different action unit. Then if you open very big, they give the largest one. They modify this for some action unit. For example, for now, they only give this as one action unit as AU25, but with 3 different intensities. They use intensity as A, B, C, D, E to say, how big you moved. If you only move a little bit, that's the intensity A. If you move a lot, that's maybe go to the E. So for that one, since the different people have the different, the amount of the movement, so that part is more difficult.
So it's like, it sounds kind of like a state, except when you're combining them, it seems hard to combine states, right? Like if they're parameters in some, facial expression parameter space, I can imagine, I got some of this parameter stretched out this way and some of this one out this way. So it's easy to understand what it means to combine.
Yeah. So that's why it's very important for how to extract the features and also how to represent the features. If you represent the feature well, then you can capture those kind of movement. If not, it's more difficult. And also for some action unit, for the lips especially, I'm thinking only based on 2D images, it's hard to detect those kind of things. We need a 3D. It's that if you do this or not. But if from the frontal, from 2D image, it looks very similar. If you have the 3D, then you can see the difference. Okay, so now after we introduce that general things, I'll move to the work we did. So we did several works here. So first one, for the facial expression analysis in a collaborative environment. That means in a lab, we can collect the data, so the people are very cooperative. We mainly have the single face, have very high resolution, and also for the expression, it's pretty much exaggerated expression. I'll show you some video. You can see why that exaggerate expressions. After that, I'll talk about the neutral face detection. Since when we do this, we have the assumption. We say, for the neutral face should be available. But in many cases, we don't have that neutral face. So how can we find the neutral face automatically? Then we move to some spontaneous expression analysis. After that, I did some performance evaluation for the expression analysis. Then we talk about the future work. Okay, now we move to the facial expression in a collaborate environment. This part of work I have done when I was in CMU with Professor Kanada and Professor Cohen. He's a professor in the psychology department. He's from the robotics computer vision guy, so we combine together to find the real applications. For the facial expression analysis, we have a video. We assume the first frame is a neutral face. Start from the neutral, then you perform the expression. So then after, from this video, we extract the features and then represent the features for the different, you see, since we have very high resolution image, we have all those kind of detailed features. When we do the recognition, we separate the upper face and the lower face. Both use the neural network-based classifier, then we get the result. And for the feature extraction, we mainly extract the eyebrows, the eyes with very detailed the iris and the up lid, lower lid, and also we put some features on the cheek. For this one, it doesn't contribute that much, especially for the baby face, because it's non-texture. It's really didn't provide that much information. But those kind of furrow provide a lot of information, and also the lip. And I will not go to the details for the algorithm, but I can show you some furrow detection. These two are very useful for the distinguish and the smile, those kind of expression. Mainly based on the edge information, we get the angle of between this one when we detect it. If the angle are bigger, mainly when you do the smile like that. And also for the lip, we combine the color, shape, and the motion information to try to track the 3 states of the lips: open, closed, and tightly closed. Here are the color distribution. You can see when the lip are in the different states, they are pretty different. One difficulty for this use the color information is for the darkened skin in color people, for the African people. Mainly their lips, the color is very similar to their skin color. So sometimes for them, we have some difficulties. For the eyelid, for the eye tracking and detection, we also try to detect the open eyes and the closed eyes. We define an open eye as if the iris is visible, then we think it's an open eye. If it's not visible, it's closed eye. And we use the edge information for the iris to try to find the iris of this. And here I want to show you after we detect the features, how can we represent that? I think that will answer part of first question. Mainly we observed for all the expression analysis, your inner corner of the eyes are pretty stable. It doesn't matter which kind of expression are you doing, the inner corner doesn't move that much. So we use the inner corner as the reference point, we get that. Then we normalize all the extracted features based on this baseline to say, okay, how much irregular brow was the parameters, and also for the different features, and also how big, how wide of this. You can see we have the blue region here and the green region there. For those regions, we mainly will try to capture the furrows, because for this region, it's try to distinguish AU6 and AU7. That means when you try to smell, if you have some furrows there, it's AU6. If not, then you cannot see that. This one, as I showed the image before, try to distinguish the discussed AU9 and AU10, if there is furrows or not. And same thing for the lower face, for the other lip features, we also normalized based on this baseline. Okay, I'll show you some examples for the tracking method. You can see the smile is exaggerated. No people really smile like this in the real life. But you can see the feature extraction. We can track the lip and also for the eye detection, the iris, like that. Here you can see for the action unit, we have the different AU combination for this feature. And also for the basic expression, it belongs to this one. They have a list to say, okay, for some combinations will belong to which basic expressions. All those kind of action units has been coded by the certificate coder. You have to get the certificate to be code this kind of action units. Here's a different expression. This is the anger. You can see the lip for the different states. We track that. Even for the eye close and open. And this kind of furrows also make the contributions to the different actions. Here's another one, the surprise. So for the surprise, mainly the mouth is wide open, and also for the eye wide open. You can see the eyebrow moves a lot. We tried that, but since most of the database, the CMU database, the CMU Pittsburgh database, are the psychology students, not that many people has the furrow on the forehead. Here another guy. You can see that they have two different expressions: disgust at the beginning, then with smile. And this is the one. And you can see their lip color are very similar to their skin color. But for most of them we can handle, but for some of them, sometimes it goes away. The lip contour goes away. Here are some examples with the head motion. You see, okay, when head moves, what it looks like. And also with the different tilt. You can see the feature attract pretty well. We also tried several. This is also recorded in the lab. I removed the chain for the case because it doesn't track that well. But you can see the iris, the tracking with all the motion. We can get very accurate result for all those kind of detailed features. Here are two videos. We can see it's a spontaneous expression. Use the camera is not in that high quality, and also with a lot of the head motion. Here's another one. And this, the interval, we ask the people watch some movie, the clips, then interview them. They didn't know we have the camera installed somewhere. So for those kind of expression, you can see it's spontaneous. The face resolution is much smaller, and also for some detail features, we cannot really catch that. You can see this one. I'll play it again. For the eye, we didn't really catch those kind of features, but the lip contour is still pretty good. For this one, the face region is about 60 by 80. For the previous one, which I shot, is about 200 by 200 or something like that. Here are the recognition results. For the lower face, we have those kind of action unit, and here are the how many times we have them in the database. Here are the recognition results. You can see in this one is pretty low, the 26. 25, 26, 27, as I talked before, is how big your mouth opened. For that one, it's most of the confusion is this thing is 26 or 25. If we combine them together as one action unit, but just give the different intensities, then this one will be much better. And also here are the recognition result for the upper face. Most of them did pretty good for the eyebrows. This 6, 5 and 6 are a little bit lower. 6 means your lower lid move up. When you smile, your lower lid move up. So all these are very subtle, difficult to detect. But overall, the recognition rate is pretty good. And here I show you the for the AU25, AU26 in the image. That's the confusion. Here is the AU5 and AU6. Those are pretty confused action unit, which we didn't do that good as other actions. Yeah.
So these are all human labeled?
Yes.
And they're based on single images?
No, based on the video sequence. For the sequence database we collected, they start from the neutral. Then you gradually perform the expression until the peak, then come down. So they have the whole sequence for that. If you only depend on the single image, for some expressions at the beginning, from the neutral, if I start to do that, it's only a little bit. They cannot code it. So they play the video by frames. They compare to the neutral to see if there movement or not. If they see that movement, then they will code the action unit.
The whole sequence is labeled as one class, one action unit?
Yes.
The whole sequence?
Yes. From with very low intensity to the peak, then come back that. They have the whole sequence. They also try to do some communication analysis. For example, for the social smile and the real smile. If you are really happy, you smile that, your smile keeps on your face. But for some social smile, if I see Zheng Yu, I say, oh, hi, I smile it. Then when he passed by, my smile come back quickly. Yeah. So they do those kind of also for the communication kind of behavior. So they try to say, okay, how long goes to the peak and then how quick come back, all those kind of things. But for the code, they do need, for the peak one, they do need, only from this image, they can say, okay, it's AO5. But for some images close to that neutral, they need to really play between the frames to see their change or not.
And are the results, the mistakes that were made, are those because the features that you're measuring, like the corners and all that stuff, didn't have enough information, or because the classifier that you used misclassified?
I think the features from that high resolution, you can see we capture pretty good. I think the main reasons because the confusion of the action unit. So all those kind of action units are coded by psychologists for human being to observe it, not really good for the computer to do that.
But
so
if a human looked at the features that were generated, they could tell the difference between 5 and 6?
Only the certificate coder can do that. For me, for some of them, I think, okay, they are very similar, they are same. If you are not trained for doing that, for the normal people, cannot distinguish those kind of things.
Do you have any data which shows the consistency between the different coders, human coders?
They have some data like that. They use the K to show that. The different coder to code some of them is about 85%. They still have 15% not agree each other. You said, okay, that's the AU6. I said, no, I don't think that's AU6. I think it's AU5, something like that. So they have, the agreement is about 85%. Still have 15% confusion. Okay, so for the previous work, we have the assumptions. For the initialization for the features, we initial them manually on the first frame, on the neutral frame. And also we assume the neutral phase is available. For the initialization already being solved by the active appearance model fitting algorithms. After I left CMU, Simon Baker, I think, is in Microsoft Research with several other people to work on that, to do the automatic fitting for the facial features. And also they extend the active appearance model to handle some head motions, try to move to the spontaneous expression. And since we have the assumption for the neutral phase, then we say, okay, if without the neutral phase, what can we do? We need to, if you give the image, I want to say, okay, is there any neutral phase or not? So that's the work. After I joined IBM, I'm continuing to work on that neutral phase detection. The purpose of this, if give you some images, and we want to find the neutral phase. And for this one, for the yellow box, we say, okay, these two are the neutral phase, others are not. This neutral phase detection is image-based, not the video-based, since we only randomly collect the images. And what we do is, we have the image input, then we do the phase detection. If we find the phase, then we extract the features. For those kind of features, I use a different algorithm as previous data, since we assume in the real application, in most of the cases, we cannot really get that high resolution image. Then based on the location feature and the shape feature, we still keep use the neural network classifier, try to find the neutral phase detection. And for this one, we only do the is neutral or not. And for the feature, since for most of the phase, we do not have that high resolution, so we reduce it to the corner of the brow and the eyes and the lip corner, without all those kind of contour, head, of those kind of detailed information. And from the later the result, you will see why we reduce it to this, since I will have some images to show you the low resolution of that. Same thing, we will, based on the eye detection, that's the baseline, to normalize this kind of corners, the width of the lip corner, and also how far from this baseline, and also for the brows. Okay, and that's the local feature. Then we have the appearance feature. We have the image, we have the edge, then we have this directional of these edges. At that time, we didn't call it hog. Hog is very hard now to do the detection, action, all those kind of things. At that time, we call it the zonal histogram features. But then I figured out it's identical to the hog feature, which people are used a lot for recent years. We have the 4 directional histogram to do that. This one shows you these 3 combination of these features to show you in which direction the edge is described. So we put this feature and the here is the shape features, and also with the geometry features together, put in the neural network. Then we find the neutral phase and non-neutral phase. Here are some results we can see. We tested on 2 databases. For the training, we use the CMU and the Pittsburgh database. We separate them to 2, only train on 1 data set, then test on another part. So we get pretty high detection rate. And also we test independent database and the EO database. This one dropped a little, but still keep pretty high detection rate.
So you use the same training data?
Only train once.
Yeah.
Use training this one, test this one, and then test a totally different database. Here are some examples for the wrong classification result. For the upper part, this part, the neutral phases are classified as the non-neutral. From the code, they say, okay, all those are the neutral phase. But our system say, okay, they are non-neutral. This one, I think maybe that's her neutral, but looks anger. This one a little bit smile. I think this true because the mustache. Yes, in the training data, we do not have that mustache. For these several images, it says the non-neutral phases, but we classify it as the neutral. And this is the non-neutral. You can see the lip a little bit apart. So they code them as AU25 like that. That's the non-neutral. but it looks, since the intensity is very small, and this one looks like a little bit small. So all the confusions are in that very low intensity expressions. So I think if we see all those are neutral, it's still acceptable for the, yes?
I'm assuming that there's a set of psychologists that do the classifications for which AU each face it belongs to. What's their percentage of hit rate if you just gave them a collection of these types of small different spaces? Mm-hmm. You know, would 95% say that that's a neutral and 5% say that that's a happy face? I mean, I'm thinking you're cutting the edge too much as far as trying to specify that this is yes or no.
I think that part, I don't know the percentage of that. I think for the certificate coder, they will definitely say, okay, since their lips are apart, then definitely have an expression there. But for the psychology people without the certification for code this, they will say, okay, that looks like neutral. I don't know the percentage for that part. Okay, so we talk about the expression in the lab and also for the neutral face detection. Then we move to the spontaneous expression. So, okay, in real life, how can we do the spontaneous expression analysis? For this kind of work, we mainly focus on two things. One is how to handle the head motion, and then how to deal with the low image quality. And we do that because they have the past data in 2003. They record the data in the smart meeting room. They have the data, and also they have the ground truth for the expression with a smile or not, like that. So you can see, compared to the collaborative environment, the intensity of those data are very low. This face region about 70 by 90 pixels on those. How can we do that? Here are the steps. They have the video. We have the video input. Instead of to do the face detection, and since there are a lot of time to move away, so we do the background subtraction. Then we do the head detection. Once we find the head, then we will say, okay, it's a frontal or not. If it's a frontal, we find the face. Then we do the feature extraction. Then we do the neutral face detection, use the neutral and other things to classify it's neutral of smile of some other things. When we do the head detection, if we couldn't find head, then we stop. If we find the head, we continue to say what's the head pose of that. Okay, here show you the background subtraction. Background subtraction mainly assume the camera is static. Here's the background. When some moving object appears, we try to get the moving object. The moving object is called the foreground. So we will find the moving object. Once we find the moving people there, we will use omega shape, the shape like omega, to say, okay, here's the head, here's the neck, the shoulder. Then we can find where is the head. All these also have one separate. We assume the people are upright. If you are bent down or something, this algorithm will not work. And also here shows you the algorithm we will do the head detection. Once we get the silhouette, we get the circle part at the top of this with this omega part. It's the several images we get for the head. Okay, once we find the head, then we will say, okay, what's the head pose? Only for the frontal or nearly frontal. When we see the frontal or nearly frontal, it means when you turn away from that plane, maybe less than 25 degrees in that. If it turns too much, we see the side wheel. But for all others, we without can see the facial features clearly. We see the others. For the facial expression, we still focus on this. For some of that, I think we can do something of that. But since from the psychologist, most of them only focus on the frontal face. We are lack of the kind of research in that part, so we still focus on this. Only for the head pose, in this frontal or nearly frontal, we continue the feature extraction. And here I show you one example for our head pose detection. You can see the original image. Here is the foreground. We did the head detection. You can see this gorge along with the head pose. And this guy, Andrew Senior, he's in Google now, cause us a lot of trouble because his board, all the color, skin color, front, up, and the back. In our training data, we do not have that. People like that. Okay, that's the head pose. And also for the feature extraction, the previous feature tracking algorithm will not work. So how can we get the feature extraction? We just use very simple binary features. You can see if we have the different threshold, we can get mainly for the eyebrow and eyes are darker than other part. So we can get this. For the threshold, if it's too high, you get this too, but this is a brow, this is the eye. So we give the automatic threshold detection, then we can get 2 pairs of this. So get both the eyebrow and the eyes. Once we get the eyes and the brows, we assume the lips is below that. Then we do the automatic search, trying to find the lip corners.
Question.
Yes.
Overall, you're all using the geometric features. I wonder, why don't you use some kind of texture feature, especially when the resolution is very low?
We have some texture features. We call it the appearance feature. I will show you later. That's we use the Gabor wavelet, try to get all those kind of changes without extract all those kind of local features. And also we compare the result to see which kind of feature work better. Here are some extract features in that smart meeting room. Detect the height, find the features. Then we use these kind of features to do that. I think this kind of shape feature kind of include in the whole face. We use this shape feature as before and also put the distance feature, use the neural network, but try to get this kind of neutral face, smile, surprise, anger, angry, and others, and also put the non-frontal. Here are some results we have. Before we talk about the result, you can see their original Groundtruth. They say, okay, smile. Since they have the video, when you turn away, they still assume it's a continuous smile. Smile, smile, all those kind of a smile. I did some modification to say, okay, since they are too confused for the system, so I modified that, okay, this is a profile, this is a side view, this smile, and also smile. For this one, I changed it to neutral. So for some of their Groundtruth, I made some modifications. Our test result are based on this modified Groundtruth about that. And you see here, for this one, we did as the surprise, not as the smile, because I think mainly because the eyebrows are raised up a lot. And here are the table for the recognition result for the non-frontal, neutral, and they have a lot of smile, but not that much other expressions. Okay, so once we try that, we have more and more questions we want to answer. So we will do the performance evaluation analysis to say, okay, which kind of facial feature play more important role for the facial expression, and also for which level of the facial resolution we still can do the expression analysis. And also if we want to do the recognition for the action unit and basic expressions, which one is easier, which one we can do better. And so we mainly compare for the facial resolution. and the algorithm for the face acquisition. That means the height pose and the face. And also we do the feature extraction, the geometry features and the appearance features. And also we compare the different recognition rate for action unit and the basic expressions. Here are table. I use that CMU database from the original image, just downsample it to the different level of the resolution to say, okay, for the face process, we can do the detection of the height pose detection. And also, can we do the face recognition? Can we extract the facial features? Can we really do the expression? Until here, I think we can do everything. But for all those, can we really do this? I'm not sure. But for the feature extraction and the expression, I think we cannot do at that level. So we also need to check in this level, which level can we really do the facial expression analysis. And for the facial face acquisition, I compared 3 algorithms. For the face detection, we used the neural network based that's developed by Henry Rowley. He worked from CMU, but then worked in Microsoft, now is in Google. Another one is integer feature-based face detector. That's famous John Viola's face detection. And also we tried our head pose detection to see can we get the comparable result for that or not. And also for the features, the geometry features, I compared the 2 ways. One is the extensive facial features. That means for the high resolution, we have all the contours. At the beginning, I show you the video with all those kind of details. Then we have the basic facial features. That's the only 6 corners, the lip corner, eyes, and the brows. That's the basic facial features. And also for the appearance features, we use it's present the skin texture and also the lips, all those kind of changes. But we use the Gabor wavelet to apply the Gabor wavelet on the whole face to try to get the appearance features. This is the extensive geometry features. This is the basic geometry features. Here are the some example for the Gabor wavelet in the different directions. You can see all these directions capture the edge in the horizontal direction. And all those kind of different directions, this is the vertical direction. We have the different orientation, combine them together, apply on the whole face. So it doesn't matter, you can extract the lip or not. Once we detect the face, we just apply it to that face region to get that.
What happened to those zonal histogram things?
That one I didn't compare to here, yes. Since if the resolution is too low for those kind of edges, you cannot really get that those kind of edges. But for this one, it doesn't matter you get the edge or not. We just apply on the whole face. I think this somehow lack the histogram of the gradients. And also here, give you the example for the expression part, the 6 or expression, and also for the action unit. Here you can see we use this one. We combine these 25, 26, 27 at that. Same thing. We have the video. Still use after we extract all the features, we still use the neural network. Then we can get the either action unit, either the 6 basic expressions. And we still use the CMU and Pittsburgh database to do the training and the testing. We just downsample the high resolution image to different level of the low resolution. Here are some results for the face acquisition. You can see until here. Both algorithms, detector 1, that's Henry Rowley's neural network based, and also John Viola's, both of algorithms can detect all the faces because the situation is very simple. Only one face on the image without any cluttered background. But for this one, both of them are fails. I think both of them work, the minimum size is about maybe 24 by 24. So if the resolution lower than that, they cannot detect it. But for the head pose detection, it surprisingly continues pretty good result until this low resolution. Here are the feature extraction results. When we do the feature extraction, for that extensive features, we can do pretty good until here. For this level intensity, we cannot track that well. That means track all the details with the contour, with all the detail information. For this level, we cannot do that. For the geometry, for the 6 points, the corners, we can do until this level, but we cannot do good at that one. Appearance features, since we can find the head, the face region, we can always apply it. Doesn't matter how confusion it is, we just apply on the face region.
So if you upsample the last column images, whether the face detector will work or not?
No, we tried that.
Even upsample it?
Yes. When you upsample it, it looks very weird. Yeah, it still cannot do that. You can see for this, when we display this, we all upsample it to the same size of this. The face detector cannot detect it. These are the action unit recognition results. You can see here. We compare the result like this. Only use the geometry feature one, the extensive one, and only use the 6 corners of that. And this one is only use the appearance features. The Gabor wavelets applied on that whole face. Then we have the combination, the appearance feature plus this feature, the extensive geometry feature, the appearance feature plus these 6 points of the geometry features. You can see here for that extensive features until in this level. It's drooped a little, but I think still keep the same level. Until this one, it works pretty well. For that geometry feature too, for these 6 points without the detailed contours, the result is much worse. But you can see, I don't think the 1%, 2% is really meaningful. But in this level, it's dropped a lot. For the appearance features, I think we get the similar result as the geometry features like we did before. It's droop, but we still can get it. Even in this level, we still can get 58% of the detection rate. When we combine them together, we can see they have a little bit increase for the accuracy, but not that much.
So how do you combine them?
We combine them means when we train the classifier, we use both of the features. For this one, we only use this one kind of features.
So this suggests that using Gabor wavelets, that's just much better.
What's the dimensionality of that appearance feature?
This one, I forgot the detailed numbers since it's pretty long.
How many wavelets?
We have all the directions. I think we have all the 8 directions, maybe about 25 degrees of the distance of that. Should be 8 directions. I forgot how many scales we used, maybe 6. 6 by 8.
Right?
On the whole face.
This whole face.
On the whole face.
Oh,
on the whole face.
It's 48.
48, something like that.
You are applying on the each pixel, right? Or not just on the center?
Let's see. No. Here. Here. You can see here. For this one, for that one, the appearance features, we based on those kind of feature points. We based on that feature points. But since for the lower face, lower resolution, we don't know where is those kind of features. Then we apply on the whole face.
The results you show in that slide.
Uh-huh.
So that was you apply this.
We
whole
apply
face
on the whole face
for all of the resolutions.
for whatever the resolutions. Yeah.
And my earlier work on Gabor is much better than geometry Gabor.
And I think for that one, since most of them are tracked pretty good, so we get the comparable result as the appearance features. But you can see this one, if we have this kind of feature, too few of them if we cannot extract the very good location features, it's much worse than the appearance features.
48. You're only using 48.
No. I think for each pixel we have the 48.
Pixel.
Yeah.
Or for each of those 18 points. So how many, like, what's
I need to recall that part. How many pixels we get. At least we have those kind of regions, since we know the eyebrows, eyes, and the lip corners. But for this one, if we do not have those kind of features, I think we apply that. I'm not sure it's on each pixel or on each region. I must separate as some, grades like that. But how many regions, how did I separate that? For now, I do not have that number in my head.
So for the high resolution faces, you're probably sure that you just...
No, for high resolution, this one, we just use those kind of points. Since we know all those kind of positions, we have these geometric features.
So for each geometrical position,
we have the...
you compute the Gabor wavelets.
Yes. But for this one, I think since we cannot get both geometry features, I think I just graded the face for each small region, the sub-block, get the facial features, get the appearance features. Here the conclusion for the performance evaluation, the head detection and head pose estimation can detect the face in very low resolution, and it's much better than the face detector. And for there is no difference in the recognition of the expression analysis when the head region, mainly the face region, is largely higher than this one. And also the geometry features, the extensive geometry features and the appearance features achieve the same level of the recognition rate. But if this part cannot do that well, appearance features will do better. That means in the future, we do not really spend that much time to extract those kind of geometry features. We can develop some good appearance features to work on that. And also for the both action unit and the 6 basic expression recognition, and seems not that much difference for us. Okay, the future work. I think the future work for now, I'm trying to focus on 2 things. One is still do the spontaneous expression analysis, but try to combine the expression and the talking by combine the video and audio. That's why I say, okay, I will do some audio work also. Because for now, when people are doing the facial expression, they assume, okay, all the facial movement caused by the expression. But for the talking, people are also working on the lip reading, the speech reading, all those kind of information. They assume all the facial movement caused by talking. But we know that's not true. In the real life, when you talk, you also have the smiles, the expressions. How can we do that to mainly improve the lip reading with the expressions? We submit a proposal to NIH, try to do the lip reading to help the deaf people about that. So I think we will work on something like that. If we have both expression and talking appears, how should we do? Another direction I want to work on is the content and the context-based expression analysis. What's this mean? The context-based, that means from the video. If we know the previous and some other thing behind that, then we can estimate some expressions even though you turn off your head from the camera. From the content, sometimes only when we know the content and the context, then we can really use the expression analysis for the emotion analysis. For the whole talk, I only mentioned the emotion at the beginning of the application, but I never mentioned any emotion. How can we use those for the emotion analysis? We must understand the content and the context. Here is the image. So which kind of expression he has from your point of view? Sad. He's crying and wipe his tears. Here's a real image. He got the championship, is so excited. Then he's crying. I think all those kind of content and also the context information will play a lot for the real application. Here are some more expressions for the championship winners. You can see all the different kind of things, but also always show you that exciting moment. How can we use all those kind of information? Then can give you some information to say, okay, you are really happy, you are excited. That's all.
Thank you.
Yes.
One problem in the spontaneous expression analysis is really the data set. There are not that many data sets available, and it's very hard to capture data set. So you mentioned one data set for the.
One data set we captured by the Salk Institute. They are doing that. They hide in the camera, so the interviewer do not know there is a camera there. But since the IRB, the confidential stuff, they cannot really release the data set. So I think the data set is a difficult problem, and also for the comparison between the different kind of job work, it's difficult. So I will mainly still focus on the controlled environment to do some lip reading stuff, but with some expression to add that. The spontaneous expression compared to the collective expression, mainly because the intensity is very, very small, and also for all the head motions. How can we do that? So if we can separate, even for the sports, we can do the segmentation about that. If we have the long video, we can say, okay, for this part of the video, this guy is happy, this guy is sad, something like that. I think that's good enough for now. Not that much people are really working on the spontaneous expression now.
Many people want to work on this, but they cannot.
But it's hard. It's hard.
They cannot get data. I mean, I talked to some people. They said that they all want to work on this, but they cannot get data.
They cannot get data, and also it's very hard to solve it. So for me, if I do that, after I get the funding support, we'll really focus on some applications.
How can you capture data?
For example, for one, I mentioned that that's for the NIH, for the deaf people. Mainly we want to provide the enhanced lip reading, give them the captions for that one. So we will capture the data in the restaurant of the meeting, the gathering room, with multiple people talking about that. Then
they usually don't have many expressions.
And they have a lot of expressions. And mainly for that one, I think we will focus on the lip reading with the different expressions. We will hire some certificate trainer to code that expressions for us. But we will not have that extensive for all the expressions. If they have smell, we have smell. Depends on, mainly focus on the lip reading, but to say, if they have 3 different expressions, we will deal with that 3 expressions. Yeah. Yes.
Seems there's a lot of similarity between face recognition and expression recognition. I was wondering if there's able to leverage some of the tech developments in face recognition.
For the recognition and this together.
Yeah, so it seems to me like, say, for example, the icon face, maybe the neutral face is more like the dominant, the one with the most significant icon value, something like that. So then all the other expressions maybe a little bit other bases around there. Just think widely, see if there's any leverage or bridge between these 2 type of.
I'm thinking for the facial extraction part can be used for the face recognition. But for the classification and the further process, this one and the face recognition are different. because for this one, we try to find the common. From the different people, we try to find the common for all this kind of movement is belong to the smile, the joy. But for the facial expression, you mainly try to find the difference. To say, okay, which part differential you and me, so I know, okay, you are doing you, I'm in me. So I think for the application part, the classifier, the discriminate part, we need to think about how to use kind of features, those kind of features. But for the feature extraction, it can be used for both application. And do you know what I mean?
Let's say you have a whole face, so each pixel connect to some kind of neuron connecting to that. And one is you can do the recognition, the other based on the movements, and then you're able to read the expression. I'm just
I think that.
For facial expression, you should try to extract the commonality among people. But for face recognition, you need to just distinguish different people.
Find the difference between the people. For this kind of classification, try to find the commonality, yes, of all the different people both have the same kind of expression, then we belong to that. And also I mentioned a little bit to use that for the person identification. That means we need, compared to this kind of general classification, you only have some very unique expression. They will say, okay, that unique expression belongs to you, not him. Then once we find those kind of unique expression, we immediately know it's you. Can use those kind of unique information for the identification.
The expressions, these are the things need to be differentiated, and that's like you try to different places.
I think CMU in Yanxi Liu, she worked on some symmetry information, try to use the symmetry information to find the people, try to identify people, since the different people have the different symmetry, even for your face. That's why when you look in the mirror, sometimes you find the asymmetry more than you just look at the person.
With respect to the images that we saw on your slide deck, were all those taken from analysis that were occurring in real time, or was this from recorded video?
For the process, it's all the recorded video from that database. But the process itself is a real-time process.
Okay.
Yeah.
And have you ever used that information to drive 3D face models for facial performance?
No, I didn't try the 3D face model. Yes?
You use the geometry feature together with the texture appearance feature. I wonder, do you think it's useful about exploring the temporal information, how the expression change over time domain?
That's very good for that. That's one direction people are trying to work on the context information. For now, for all the features, for all the results I presented today, even though we use the video to do the tracking, but for the recognition, it's still frame-based. We didn't use any temporal information in there. That's why for the spontaneous one, for the smart meeting, they code that as a smile when the people move out because they use the video information. They say, okay, that guy still smile. But since we are doing image-based, the classification is image-based, then we cannot recognize that as a smile.
The simplest one could be just integrated over time.
Yes.
You can do the frame by frame recognition, but you can integrate over time.
Yes.
That will improve the.
In that one, we at least we can improve the result. Even for the single frame, yeah. We did the wrong recognition. But since it cannot be, okay, smile, then side, then smile, yeah. Then we can absolutely improve the overall recognition rate.
Any more questions? Okay, let's thank India again.